Hello, hello everyone. All right. How's assignment 4 going for you? All right, good. So today is going to be on assignment 5, in fact. Okay, so we're going to talk about, but it's going to be on past paper A-level questions. Okay, so we have David Vaccaro joining us soon, hopefully. And yeah.
Oh, I was not connected. Okay. Hopefully you should hear me better now.
Hello, everybody. Sorry I was a little bit late joining. I've got a new computer and I just needed to enter the Wi-Fi key. I hope everyone has had a really nice Christmas and is looking forward to tonight's webinar. Tonight's webinar is a little bit different to other sessions in that we're looking more at actual A-level questions. Okay, so I think that will fit well with the stage that many of you are in. Probably lots of you have got mock exams coming up, and will therefore benefit from looking at A-level questions. Does mean that it might be slightly less like honed towards admissions test practice. What I would be keen to know is if there's any particular questions or topics that, because obviously there's, with the whole of maths and further maths A-level to go through, it's not going to be a chance to go through everything. So if people could put in the chat any topics, question types that they feel would they would particularly like to go over tonight, then that would be really useful for me. Or if you feel really brave, feel free to unmute yourself. Okay, let's have a look at the chat. Oh, wow. Vectors, chi-squared tests, and statistics too. I haven't got any questions prepared in that area, partly because not everybody does those modules. We'll see what we can do later on. Vectors should certainly be able to help you with. Right, let me share my screen. And this sheet, I think, has been shared with you. This is a collection of exam style questions. And I've tried to source them from a variety of places. And let's start with this one, which I really liked from a Cambridge entrance paper back from the 1960s. I managed to kind of convince myself that this counted as a A-level question. Maybe I'm sort of just showing off, well, not showing off, just trying to sneak in admissions test style questions. But I just thought this was a lovely, lovely question. So it says, discover a general formula of which 1 cubed plus 3 cubed plus 5 cubed is equal to 9 times 17. And 1 cubed plus 5 cubed plus 7 cubed is 16 times 31. Now, what I would invite you to do in the chat, if you can spot it, enter the formula into the chat. But let's imagine that you couldn't see what the rule was. The natural thing to do would be to see if, maybe this numerical information is not enough. Now, we're obviously looking at the sum of the cubes of odd numbers. So we could just look at 1 cubed plus 3 cubed, which is 28, and that is 4 times 7. 1 cubed plus 3 cubed plus 5 cubed plus 7 cubed is given as 9 times 17. 1 cubed plus 3 cubed plus 5 cubed plus 7 cubed is given as 16 times 31. Now, maybe we're still struggling for numerical information. So the next number we would add would be 9 cubed. So 9 times 9 times 9, which is 729. 16 times 13 is, sorry, 16 times 31 is 480 plus 16, which is 496. Lovely, perfect number. And then we add 7 to 9 and 15, 12, 1, 2, 2, 1, 2, 2, 5. Now, what factors, in terms of looking for patterns, what factors do we have so far? We have a factor of 4, a factor of 9, a factor of 16. Now, these look like the square numbers. 7, 17, 31. It's maybe less clear cut what they are at the moment. So let's do 25, which is the next square number, into 1, 2, 2, 5. Okay, so that's 4 remainder 2. And so the odd bracket is, I think this is going to be 41. Yeah, because 40 25s are 1,000, then we've got one more. So we've got 25 times 41. Any offers in the chat for the next term in the sequence of 7, 17, 31, and 41? Okay, well, it's worth noting. Oh, we've got nothing in the chat. Oh, interesting. I thought I was going to open it and have a sea of suggested formulas based on these two examples, but no, we certainly do need the numerical formulas. Well, an interesting question is to ask, what type of sequence are we expecting for the sum of these cubes? Okay. Now, if you think about special sums, we know that if we do the sum of the cubes, it's the square of the triangle numbers. The triangle numbers are n times n plus 1, which are quadratic. So the sum of the cubes, we'd expect a quartic. So we'd expect 7, 17, 31, 41 to be a quadratic sequence. And we know that quadratic sequences have a constant second difference. So what I'm expecting is I'm expecting that if I look at the difference of this sequence, that would form an arithmetic progression. So 7 to 17, the difference is 10. 17 to 31, the difference is 14. Oh, wait a minute. What's 25 into 1225? Sorry, because 41 would be 1025. 25 into 1225. Here we've got 122. The remainder is 22. So this is 4. And then this is 5. So this should be 4. No, this is 225 is 9, so this is 49. So the sequence goes 10, 14, 18, and that is nice. That's got that does indeed have a constant second difference, and the second difference is 4. Now I know that my standard quadratic, my standard sequence of squares 1, 4, 9, 16 has got common second difference of 2 because the differences are the odd numbers. So the quadratic term in this, my daughter has just come home. Hello, Lottie. So the quadratic term in this sequence is 2n squared. Okay, now the sequence 2n squared will go 2, then 8, then 32, then 64. And then what I need to make my second factor is 5, then 9, then sorry, 2 times 3 squared is 18. So this goes 18 and then 32. And then to get from 18 to 31, I need a 13. To get to 32 to 49, I need a 17. So this is now, I can see this is an arithmetic sequence. 5, 9, 13, 17 has got formula 4n plus 1. So the formula of 5, 9, 13, 17 is 4n plus 1. So what I now have for this second factor, this sequence 7, 17, 31, 49 has formula 2n squared plus 4n plus 1. So the 2n squared was designed to get the common second difference of 4. And then the 4n plus 1 gives me the difference. So let's just check this. So I'm suggesting that the factor 7, 17, 31, and 49 has got formula 2n squared plus 4n plus 1. Well, when n equals 1, this gives me 2 times 1 squared plus 4 plus 1, which is 7. When n equals 2, this gives me 2 times 2 squared, which is 8, plus 4 times 2, which is another 8, plus 1, which is 17. When n equals 3, it gives me 2 times 3 squared, which is 2 times 9, which is 18, plus 4 times 3, which is 12, plus 1, which is 31. So this really is the sequence 7, 17, 31. Okay, so lovely little question. And that first part, in some sense, the content is just GCSE sequences. Yeah, we just need to generate this sequence 7, 17, 31, 49, generate its formula. I suppose a little bit of intuition we needed to get the formula was that it was a quadratic sequence. So what I now think is that the sum of the first n odd numbers is n squared. Oh, wait, yeah, n squared times 2n squared plus 4n plus 1. So the formula that I think I've proved is that 1 cubed plus 3 cubed, and then the nth odd number will be 2n minus 1 cubed is equal to n squared times 2n squared plus 4n plus 1. Okay, so that was the first part of that question. And what I've done to there is I've found the equation of the formula. Oops. And what I'd like you to put into the chat now is, how would I now do part B of the question? Oops. How would I now do part B of the question, which would be to prove this formula? Excellent, proof by induction. Well done. Well done, Adam. Just also in the chat, how does this question differ from a normal A-level question on proof by induction? What is it rather disappointing about A-level that you're never asked to do in a proof by induction question? But which you have been asked to do here. Okay. In a normal A-level question of proof by induction, you would always just be given the expression that they want you to prove. Okay, the extra step here was actually to find the formula. And I wanted to start with proof by induction because this is a very useful topic to go through in a webinar, because it's very useful to have a model solution. So here is my claim. That 1 cubed plus 3 cubed plus ... 2n minus 1 cubed is equal to n squared times 2n squared plus 4n plus 1. Now, in order to prove a proof by induction, I start with the base case. And what I will do is I will verify, and that's the right verb, that star is true when n equals wait a minute. My sequence 5, my 4m plus 1 sequence is starting from the second term in the sequence. So it should be, so the formula should be 4n minus 3. Because I really should have had a term at the beginning, which is just 1 cubed is equal to 1, which is equal to 1 times 1. So my first term in the sequence, this numbering is off. This is actually the second, third, and fourth term. So the bracket here is actually 2n squared plus 4n minus 3. Okay, so let's verify that this formula is true when n is equal to 1. So the left-hand side is just the sum of the first one odd number, so it's just 1 cubed, which is equal to 1. The right-hand side is 1 squared times 2 times 1 squared plus 4 oh no, my sequences. No, I need to do a little bit more surgery to correct this second bracket. So the 2n squared plus 4n plus 1 is the correct sequence starting, if I number the sequence from term 2. So the sequence which I want is 2 times n minus 1 squared plus 4n minus 1 plus 1, which is 2n squared minus 2n plus 1 plus 4n minus 4 plus 1, which is 2n squared plus 2n minus 3. And now the right-hand side is 2 times 1 squared plus 2 times 1 minus 3, which does indeed equal 1. Okay, so the result is true when n equals 1. The next stage of a proof by induction is to do the inductive step. Now, the right verb for the verifying the base case is verify. So this is the base case. For the induction hypothesis, the correct verb is to assume. So what I'm going to do is assume that star is true when n equals k. So 1 cubed plus 3 cubed plus ... 2k minus 1 cubed is equal to 2k squared plus 2k minus 3. Now, under this assumption, by adding 2k plus 1 cubed to both sides, 1 cubed plus 3 cubed plus 2k minus 1 cubed plus 2k plus 1 cubed is k squared, 2k squared plus 2k minus 3 plus 2k plus 1 all cubed. Let's open up all of the brackets. So we get 2k4 plus 2k cubed minus 3k squared. To open here, I want to use the binomial expansion. So I write 8k cubed plus 12k squared plus 6k plus 1. And if I simplify, this is 2k4 plus 10k cubed plus 9k squared plus 6k plus 1. Now, what I hope is that this has got the correct factorization. So in particular, I hope that k squared plus 1, k plus 1 all squared is a factor of this expression. So let's see if it is. K plus 1 squared is k squared plus 2k plus 1. And what I'm going to try and do is find a second factor which will make this bracket. So to get the 2k4 term, I put a 2k squared. So that gives me 2k4 plus 4k cubed plus 2k squared. I now want an extra 6k cubed term. So I want an extra 6k here to give me 6k cubed. That gives me 12 k squared and 6k. minute, something has. Eight, 4 times 3. This is not quite. I'm still a little bit worried about this second. I'm still a little bit worried about this second bracket. So the sequence that I really want is 1, 7, 17, 31, 49. My 2n squared would be 2, 8, 18, 32, 50. It's a much simpler second bracket. So the second bracket is actually 2n squared minus 1. Sorry, so this second bracket is 2n squared minus 1. The base case still checks out. But now the induction hypothesis requires a 2k squared minus 1. And we get a simpler term. So the induction step is now 2k squared times, oops. So the induction step is now k squared 2k squared minus 1 plus 2k plus 1 cubed, which gives me 2k4 minus k squared plus 8k cubed plus 12k squared plus 6k plus 1, which is 2k4 plus 8k cubed plus 11k squared plus 6k plus 1. I again hope that k squared plus 2k plus 1 is a factor. 2k squared is my first bracket. Now to make the 8k cubed, I need an extra, I've already got 4, so I need another 4k cubed. That gives me an 8k and a 4k. To now make the 11k squared, I've got 10k squared, so I just need one more. So that gives me another k squared. I've already got 4k, I want to make 6k, so I want another 2k, and then I want a 1. And so this time the factorization really does check out. So under the induction hypothesis, one cubed plus 3 cubed plus 2k minus 1 cubed plus 2k, oops, plus 1 cubed is now k squared plus 2k plus 1, that's the first bracket. And then the second bracket is 2k squared plus 4k plus 1. Now, what we hope, okay, we hope that this has got the right format of the formula that we're trying to prove. So the n squared times 2n squared minus 1. But let's look at this k squared plus 2k plus 1. That's exactly k plus 1 all squared. The second bracket, if I write it as 2k squared plus 4k plus 2 minus 1, then this first part is k plus 1 squared. The second part is 2 times k plus 1 squared minus 1. And that has exactly the same format as what we're trying to prove, except now where the n was before, we've got a k plus 1. So what we can conclude here, therefore, under the assumption that the result is true when n equals k, it is also true when n is equal to k plus 1. The result is true when n equals 1. Therefore, it is true for all n. Okay, so by mathematical induction, one cubed plus 3 cubed plus ... 2n minus 1 cubed is n squared times 2n squared minus 1. Okay. What have we learned along the way? Okay. And I didn't do this deliberately, but we've seen that questions like this might not go smoothly. Okay. Especially in a question like this where we're not given the proof by induction. I needed to do a little bit of work to finally hit upon the right formula and then do the proof by induction. But this gives a good indication of the difference between the questions we're going to do now, which are questions from A-level papers, and this question whose source was a Cambridge scholarship paper. Okay, let's move on and let's do the next question, which is on complex numbers. Let's see how this one goes. So part A, find a simplified expression for e to the half I theta, which we know is cos half theta plus sine half theta I. And they want me to add that to e to the minus half I theta. Now cosine is an even function. So the cosine term remains the same when the theta is replaced by a minus theta, but sine being an odd function is replaced by minus sine half theta. And when I add, gives e to the half I theta plus e to the minus half I theta. The sine terms cancel, so this is just 2 cosine half theta. Notice we shouldn't be at all surprised to get a real result because we've added a complex number and its complex conjugate. It then says, hence, establish this expression. Well, what we notice is that if we want to turn this term into 1, we can just multiply both sides by e to the half I theta. And now the first term in the expression, the e to the half I theta, will just become e to the I theta. The second term will become 1, and we get 1. So we get 1 plus e to the I theta is equal to 2 to the is 2 cos half theta times e to the half I theta. It might be interesting at this point to think about the or otherwise. And the or otherwise, or there's many or otherwises, but what we could do is we could think entirely geometrically and think about e to the I theta plus 1 as being a complex number, which is the real number 1 added to a complex number with modulus 1 and argument theta. And now if we were to do a little bit of angle chasing, we would realize that this angle in here is pi minus theta. The triangle is isosceles, so these two angles are equal. So this angle here is, this angle here, phi, satisfies 2 phi plus pi minus theta is equal to pi. So phi is equal to theta over 2. So what this diagram establishes is that 1 plus e to the I theta has argument theta over 2. To find the modulus would be this length. And to find the modulus, I could just drop a perpendicular here and then notice that the distance to the midpoint is just cos half theta. Yeah, because if I just zoom in on this triangle, here's the right angle, this length is 1, this angle is a half theta, and so the adjacent side is cos half theta. So what we can see from the diagram is that the modulus is 2 cos half theta. And that makes, so now this expression here makes perfect sense because this 2 cos half theta is the modulus and the half I theta is the argument. Okay, but it's much easier just to use the original trig identity. It then says the expressions C and S are defined, and then C and S are expressions involving binomial expansions. And part B invites us to find an expression for C and S, and then to prove some identity. Any suggestions in the chat about how part A might be useful? What mathematical operation, if I know that 1 plus EI theta is equal to 2 e to the half I theta cos half theta, what mathematical operation is most likely to produce these binomial coefficients? And I'm expecting a string of comments in the chat, because the clue really should be that if I'm going to get binomial coefficients, I really want to look at the binomial expansion. So let us consider the binomial expansion of 1 plus e to the I theta to the n. Now, on the one hand, this is just 1 plus n choose 1 e to the I theta plus n choose 2 e to the I theta squared, which is 2I theta, plus n choose 3, which is e to the I theta cubed, which is 3I theta, all the way up to n choose m, e to the n I theta. Now, does this look like anything that we have? Well, we know that each of these complex exponentials, e to the I theta, e to the 2I theta, e to the 3I theta, e to the ni theta, that all of them can be written as in terms of their real and imaginary parts. So if I split up all of these complex exponentials, I can write 1 plus e to the I theta is equal to 1 plus n choose 1 cos theta plus I sine theta plus n choose 2 cos 2 theta plus I sine 2 theta plus n choose 3 cos 3 theta plus I sine 3 theta all the way up to n choose m cos n theta plus I sine n theta. Now, gathering the real parts together just gives me everything with a cosine in it. And gathering everything imaginary just gives me all the terms with a sine. And so looking back at the question, the term with all the cosines in it, which is my expression here, is what was called C. So I can write 1 plus e to the I theta is equal to C. And then in a very similar way, if I look at the imaginary part, I just get all the expressions with the sine thetas and the binomial coefficients. And that's exactly the same expression, and that is S. So e to the I, 1 plus e to the I theta to the power of n is just C plus I S. Now, the natural thing to do is to use the expression, the expansion from part A, and to recognize that we could also take the nth power of the expression on the right. So on the other hand, one plus e to the I theta to the power n is just 2 cos half theta e to the half theta I to the power n, which is 2 to the power n cos to the power n of a half theta, and then the nth power of e to the half theta I is e to the half theta I. But I can now play the same game and split this complex exponential, and in this case it's e to the half n theta I, into its real and imaginary components. So I have that it's equal to 2 to the n, cos n half theta, and then multiplied by cos to the half n theta plus I sine to the half n theta. But now I can equate real and imaginary parts. So I know the real part is C, and that is 2 to the n cos n half theta cos half n theta. And the imaginary part is 2 to the n cos n half theta sine to the half n theta. And all I've done there is I've equated real and imaginary parts. So where am I up into in the question? Well, I've found expressions for C and S. I now just need to get the ratio of S and C. So if I do S over C, the modulus of those two complex numbers, sorry, both of those two real numbers contain the 2 to the n cos half theta to the power n. But where they differ is the S has sine half n theta and the C has cos half n theta. And that is equal, so this is equal to tan half n theta. Just for out of sanity, or just as a sort of sanity check rather, we note that because 1 plus e to the I theta has argument theta over 2, 1 plus e to the I theta to the n has argument n theta over 2. But if 1 plus e to the I theta is equal to c plus is, and the argument is n theta over 2, then we know that e to the I theta plus 1 to the n is a complex number which looks like this. It's got real part c and imaginary part s. Its argument is n theta over 2. So if we just do simple trigonometry, we can see that the tangent of n theta over 2 is the opposite, which is s, over the adjacent, which is c. And so this formula here for s over c makes perfect sense. Okay, so big meaty complex numbers question. What was that, an 11 marker? Does anyone have any questions about that question or the first question, or are people happy for me to go on? If you're happy, just put a thumbs up into the chat. If you've got any questions, put the questions into the chat. Oh, we've got some thumbs up coming in, which is nice. Okay. Notice again that with that question, there were some technical challenges, but it was conceptually much easier than the first question. And in the first question, the bit which made us sweat the most was the part finding the formula. And I think that's quite a good illustration of the difference between A-level questions and entrance paper questions, because it's the finding the formula in a proof by induction question which is never asked. Okay, let's move on. And in the interests of time, I am going to take the advice of people who wanted a vectors question. So, because I think vectors can indeed be a challenging question, can indeed present challenging questions. So let's have a look at this question. A plane pi has equation 2x plus y plus 2z equals 3. A line L has equation r equals 3 minus 5, 1 plus mu 1 minus 2p. And the acute angle between the line and the plane pi is 30 degrees. Find the value of p. So in the chat, suggest what you would do first. What would be the first bit of the method of solving this question? And what I'm expecting is that there will be a resounding vote for drawing a diagram. So if we draw the diagram, we've got a plane which I might as well draw flat in the ease of making it easy to draw. And then we've got a line, L. Okay, and the line will obviously hit the plane somewhere, not quite sure where. And we're asked to find this angle theta, which is the acute angle between the line and the plane. Is there any angle is there any other vector? Is there, from this equation of the plane, 2x plus y plus 2z equals 3, is there any vector that we're able to find out what it is, and any vector which might be useful to know in order to solve this question? Well, hopefully you recognize this equation of the plane, 2x plus y plus 2z equals 3, as a dot product, x, y, z, dotted with 2, 1, 2 is equal to 3. And what you also hopefully know is that if you dot the vector equation of a plane is given by r dotted with the normal vector is equal to a constant. So the constant is 3, but this vector 2, 1, 2 must be the normal vector. So what we know is that the normal vector here, n, is 2, 1, 2. What we also know is if we look at my line, we know that this vector, the 1, negative 2p, is the vector which points in the direction of the line. So we know that vector. What we're also given in the question is that the acute angle between the line and the plane is 30 degrees. So this angle theta is 30 degrees. So this angle in here is 60 degrees. So what we can now see is that the vectors 2, 1, 2 and 1, negative 2p make an angle of 60 degrees. Now, if you could put it into the chat, what bit of theory could we now use to make a relationship between the two vectors if we know the angle between them? Well, something which we know is that the dot and cross product give us relationships between vectors and the angles between them, and it's considerably simpler to use the dot product. And we know that if we dot two vectors, then the result is the product of the moduluses multiplied by the cosine of the angle between them. Now, what can we do easily? We can easily dot the vectors 2, 1, 2 and 1 minus 2p. We just multiply the corresponding components. So we do 2 times 1 plus 1 times minus 2 plus 2 times p. So we get a dot product of 2p. Okay, so this dot product A dot B is 2p. What we can also find quite easily is the moduluses of these two vectors. So the modulus of 2, 1, 2 is the square root of 2 squared plus 1 squared plus 2 squared by Pythagoras. And the modulus of 1 minus 2p is 1 squared plus 2 squared plus p squared. So we found the two moduluses. The last bit of the dot product is the cosine of the angle between them, but we know the angle between them is 60 degrees, so we need to multiply by cosine of 60. But cosine of 60 is a nice special value, that's a half. So now we can neaten everything up a little bit. So we get 2p is equal to the square root of 4 plus 1 plus 4, which is 9. So that's 3, times the square root of 5 plus p squared, times cos 60, which is a half. And that's all equal to 2p. So therefore 4p is equal to 3 times the square root of 5 plus p squared. Okay, how are we going to solve this equation? Well, we square both sides, okay, to get rid of the square root. So we get 16p squared is equal to 9 times 5 plus p squared. And we therefore get 16 minus 9, 16p squared minus 9p squared is 7p squared is equal to 45. So p squared is 45 over 7. So therefore p is equal to the square root of 45 over 7 plus or minus. Now, if we read the question carefully, it says find the value of p. But at the moment, we've only rounded p down to either being the positive square root or the negative square root. Okay, let's check if people are still awake and happy and following. So we'll do a vote. Who thinks that I should take only the positive square root? Who thinks I should take only the negative square root? And who thinks that I should take both square roots? We've got a vote for both. We've got a vote for positive only. So how are we going to resolve this? Well, let's look back at the equation we were trying to solve. So the equation that we were trying to solve is here. The equation that we're trying to solve is that, or a neater version of it, an equivalent version, is worth putting in these logical connectors. Up to here, everything is if and only if. So the equation we're trying to solve is 4p is equal to 3 times the square root of 5 plus p squared. When we square both sides, we lose the backward implication. We only have the forward implication. Yeah, because a equals b implies that a squared equals b squared, but a squared equals b squared does not imply that a equals b. Okay, because a could equal minus b. So it's at this step here where we might have introduced extraneous solutions. And so to decide which route to take, we need to look back at this equation. And because a square root is always positive, so root 5 plus p squared is greater than 0. So p is greater than 0. Okay, so the only square root we take is the positive square root of 45 over 7. Okay. I feel this question is a little bit, whenever I've done A-level marking, the thing which is very ambiguous to mark are candidates who are so bad that they forget at this point that they need to consider the positive and the negative square roots. Okay, so if a candidate just writes p equals root 45 over 7, you don't know if they've considered both roots but then rejected the negative root, or they've realized that at this point they've got 2 roots and then fully understand why you reject the negative root. Okay, you know what advice I'm going to give is make sure that you show enough working okay, you show that you've considered both roots and then rejected the negative root. Okay, that shows that you're getting this question right rather than forgetting the negative root. Okay, and I've deliberately put that in as an IB question because the IB tends to be a little bit better at examining sort of logic within questions. Okay, is everybody happy with that vectors example? If you are, put a thumbs up into the chat. Yeah, thumbs up. Good, let's move on. And we're running a little bit short of time. This one's bound to be good in the sense of hard. So this is from an AEA paper, which is an exam which sadly doesn't exist anymore, but used to be at a level a little bit above A level. So let's have a look at this one, problem number 17. It'll be less hard than the very first question, which was from Cambridge scholarship paper. And that one, as you remember, made me sweat. In retrospect, I sort of feel bad about that question. Okay, so it says this one, the points on the curve C satisfy x plus 1, x plus 2 dy by dx is equal to xy. The line y equals 2x plus 5 is a tangent to the curve at P. So we've got this crazy curve, which I'm not even going to attempt to sketch, but I'll just draw some curve. And at the point P, the tangent is 2x plus 5. So can anyone give me 2 facts about the point P? Okay, put them into the chat. Well, the first thing which is obvious about the point P is that it lies on the line y equals 2x plus 5. So at P, y equals 2x plus 5. The other thing which is clear about the point P is that at the point P, 2x plus 5 is a tangent, so the gradient of the curve is the same as the gradient of the line. So at P, we can say that dy by dx is equal to 2. Now, even though we've got no nice expression for the curve C, what we can do is we can substitute these 2 facts back into the equation. So what we know is that x plus 1, x plus 2, times dy by dx, which is 2, is equal to x times y, which is 2x plus 5. And now we can just open up all the brackets. So we get 2x squared plus 6x plus 4 is equal to 2x squared plus 5x. And the 2x squareds cancel, and that's nice because we were told that there was just one point P, and I was worried we're going to have two roots, and we end up with x equals -4. Reading the full question, we know that we need to find the coordinates of P. So how are we going to find the y value? But we know that at P, y equals 2x plus 5. So y is equal to 2 times -4 plus 5, which is -3. So P is -4, -3. Okay. Nice question. Notice that it's a chunky 7 marker. Notice that it's also, you know, where the marks are recognizing, and this is, you know, because this is AEA rather than A level, it's a little bit less signposted, but a lot of the marks are recognizing in a slightly non-obvious way how to relate this tangent at P back to the functional relationship or the differential equation for the curve. I'm aware I did that 7 marks quite quickly. Can I just check in the chat that everyone's happy with part A before I move on to part B? So just put a thumbs up in the chat if you're happy. Yep. Good to see some thumbs up. So let's go back now to part B, where we're asked to find the equation of the curve C, giving our answer in the form y equals f of x. Well, I suppose the clue from earlier was I mentioned that this was this equation that was given for C is a differential equation. Now, once you get to university, you're going to have enormous amounts of fun solving differential equations, and you're going to solve differential equations using a vast array of different techniques. Increasingly, you will solve differential equations numerically because some of them become impossible to solve. But at your stage, really, most of you know one and only one way of solving differential equations, which is to separate the variables. So let's do that. Let's put all the y's together by dividing by y. So we get dy over y. I take the dx over to the other side, in inverted commas, by multiplying. And then I divide the x plus 1, x plus 2. Now, this expression that I've written down here so far is nonsense. Yeah, because you can't have these just expressions dy, dx on their own. They don't live in the wild. But what I can do to write down an expression that is meaningful is I can just integrate both sides. The left-hand side integrates itself. It's just the natural logarithm of the modulus of y. And the right-hand side is a little bit more tricky. No, notice I'm getting ahead of myself in terms of being careful. The reason I put the modulus of y rather than y is I'm already looking to a point which I know is on the curve where y is negative. So I'm not going to be at all surprised if, you know, that I end up, well, in many ways, I know that I'm going to be taking I'm going to be taking the negative branch, because otherwise I'm not going to be able to have -3 on the curve. To integrate the right, x over x plus 1, x plus 2, put into the chat what method you think is going to be necessary in order to be able to compute this integral. At the moment, it's not in a nice form. But x over x plus 1, x plus 2, we should be able to write in partial fractions. And if I multiply up by the numerator, the denominator, I get x is equal to a times x plus 2 plus b times x plus 1. And there's all sorts of ways of finding a and b. One thing we could do is we could just substitute in, and this x equals -1 to eliminate one of the brackets. So we get -1 is equal to a. If we play the same trick and put x equals -2, we get -2 equals b. So we get b equals 2. So my partial fractions expansion is 2 over x plus 2 minus 1 over x plus 1. Okay. Always worth checking. Yeah, I can do that in my head and it works. So I've got ln of y is equal to the integral of ln of mod y is equal to 2 over x plus 2 minus 1 over x plus 1 dx. And now I can write ln of y is equal to 2 ln of x plus 2 minus ln of x plus 1. And now what I can also include is I need to include my constant, and the natural way to include my constant is to write it as ln of a, and now I can gather and get combine everything using the law of logarithms as ln of y is equal to x plus 2 squared a over x plus 1. And because the logarithm is 1-to-1, I can just take the natural logarithm of both sides and write that y is equal to a x plus 2 squared over x plus 1. Now I'm going to ditch the modulus because I can just take the constant a to have the right sign to make y positive or negative. Right, so I've got I'm very close, okay? So I've got y equals f of x, but I've still got this slightly annoying constant. Any suggestions of what I can do to now find the value of this constant or parameter of integration a? So I've got y equals a times x plus 2 squared times x plus 1. How can I find the constant a? Well, earlier on in part A, I found this point on the curve. Okay, I know that when x is equal to -3, y is equal to -4. So -4 is equal to a times -1 squared over -2. So a is equal to 8. So y is equal to 8x plus 2 squared over x plus 1. Now, this was a big, meaty question. Okay, it was a big 12 marker. Okay, but we did that 12 marker quite quickly. What might not be at all a bad idea to do, how could we check whether we've got the right answer, whether this y equals 8x plus 2 squared over x plus 1 is the correct answer? Well, we know that it should satisfy the original differential equation. Okay, so if we had time at the end of an A-level exam, okay, so if and only if there were time, we can check. So y is equal to 8x plus 2 squared over x plus 1. dy by dx, we can differentiate using the quotient rule. So u is 8x plus 2 squared. U dash is 16x plus 2. V is x plus 1. V dash is 1. So dy by dx is vu dash, which is 16x plus 2 x plus 1, minus uv dash minus 8x plus 2 all squared, all over v squared, so all over x plus 1 squared. Let's simplify this a little bit. We can take out a factor of 8x plus 2, and that gives us 2x plus 2 in the first bracket, take away x plus 2 in the second bracket. So we get dy by dx is 8x plus 2 times x over x plus 1 squared. What does the differential equation involve? It involves the term x plus 1, x plus 2 dy by dx. So x plus 1, x plus 2 dy by dx is equal to 8 x plus 2x x plus 1 squared times x plus 1 x plus 2. That's just the y times those two brackets, and that gives me 8x plus 2 squared over x plus 1 times this extra x. But this term that I've picked up here, the 8x plus 2 squared over x plus 1, that's just identical to the y. So what I've got is that x plus 1 x plus 2 dy by dx is equal to xy, which is what I wanted. A second thing I can check, having found dy by dx here, I can find the value of dy by dx when x equals -4, which is my point P, remember, and that is equal to 8 times -2, -4 over -4 which is plus 1, which is -3 all squared, which is 9. Why is that not quite checking out? Oh, sorry, when I found my constant of integration A, I had got my P the wrong way around. I should have had at x equals -4, y is equal to -3. And if I had done that, I would have got -3 is equal to A, -4 plus 2 squared, so that's -2 squared, over -4 plus 1, which is -3. So I would have got A is 9/4. And that will have given me, sorry. And so that will have given me, instead of an 8 on the top, that will have given me Y is equal to 9/4 x plus 2 squared over x plus 1. Okay, let's convince ourselves that that doesn't affect the first part of the checking, because the 8 just stays as a constant. But if I replace that 8 by 9/4 in my dy by dx, when x equals -4 this time, dy by dx is 9 times -4 plus 2, which is -2, times -4 over 4 times -4 plus 1, which is -3 squared, which is 9. And when I simplify here, the 9s and the 4s cancel, and I get dy by dx is equal to 2. So what I can see here is that at x equals -4, dy by dx is equal to 2. And this makes me happy, okay, because I can see that the gradient at P is now 2, and 2x plus 5 can therefore be a tangent. So what was the moral here? Okay, and I swear that I didn't do that deliberately. That would be far too difficult to do. But that last section shows the importance of checking. Okay, because in AEA questions, step questions, and that Cambridge entrance paper at the top, okay, the questions are quite sophisticated and there's more scope for error. Notice in the A-level questions, those tended to go a little bit smoother. Okay, so I hope that was a useful webinar. I hope that went through the right sort of questions for you. I will try and dig out some statistics options questions for the next pure maths one, because that's what people asked for at the start. I will just go back to the chat and see if anyone's got any final questions or comments before saying goodbye. I'm just looking in the chat now and I can see using partial fractions was correctly suggested for that integral. Okay, any final questions? Okay, so as a recap, in the first question, we huffed and puffed a little bit, but we eventually found that the general formula was n squared 2n squared minus 1. Once we got to that formula, after a few wrong attempts, we were able to do the proof by induction. We then did a nice complex numbers question with a slightly disguised binomial expansion, equated real and imaginary parts, and found a nice trig identity. We then did a lovely little vectors question, which showed the importance of drawing a diagram and toggling between Cartesian and vector equations of planes. And then we finished with an AEA question, a big 12 marker involving a differential equation, but also a slightly non-standard way of finding a point on a curve. Okay, so I'll check the chat, but if there's no questions or comments, we will finish it there. Yeah, so good luck with the rest of the questions on that sheet. Okay, goodbye, everybody.